Welcome back. In the last few lectures, we were discussing about thermodynamic properties from volumetric data. We will continue this discussion, and in particular this lecture, we will look at the fugacity of pure liquids and solids. Okay, now often many times we would like to calculate the fugacity of liquid, particularly fugacity of pure liquid at temperature Tp. So, since is let us say liquid is I in this case. Now, if you would like to evaluate this, we can make use of the earlier expression which we have evaluated for the pure liquid system, that is ln Fi by P pure. Okay. This is equal to 0 to P compressibility factor minus 1 by P dP. Okay. But in this case, what we are going to do is we are going to break this integral from 0 to P to two parts. Okay. This is mainly because what we are interested is basically the compressed liquid state or the point. So, let me first draw a generic phase diagram here. So, this is the pressure P against molar volume. Okay, so this is typical two phase region, and this is basically kind of liquid vapor region. Okay. Now, since our interest is somewhere here, this would be our point of, let us say, interest. Okay. And the corresponding line I can use solid line here, and so this is basically isotherm. So, our point of interest is this point, of which basically we are trying to calculate the fugacity. Okay. So, now this is at P and T. Okay. This is the corresponding P is here, but this point corresponds to P I for the pure system, I sat. Okay. So, we can break this expression, okay, because this expression in two parts. So, the left hand side still remains the same. Okay. But now, I will break it into Pi sat from 0 pressure, okay, which is somewhere way down, okay, way down here. It will be 0 pressure from here till the point we reach P saturation. I can actually write this also as plus Pi sat P z minus 1 P by dP. I can simplify this expression also in terms of the molar volume directly. Then in that case, the equation will be R T Fi L, let us say P, that is going to be 0 to Pi sat, and here now we have Vi. So, this is basically rearranging this, because Z is nothing but PV by RT. So, this second term is Pi sat P Vi minus RT by P dP. Okay. Now, this part we can relate to the fugacity at saturation condition, since RT Fi or F pure I sat T, but now corresponding to P sat, that means this point corresponding to this point would be P sat. Okay, this is going to be simply 0 to Pi sat, I will put Pi here, Vi minus RT by P dP. So, this term is in fact by definition. Okay, from here we can directly get, putting P as P sat would indicate this Fi is basically corresponding to saturation condition. Okay. Now, we plug this expression back here, because this for generic Tp, this part is nothing but RTF pure sat. So, let me write down here RT from here, RT FIL Tp by P, this is nothing but RT, this term is going to be RT F pure I sat T Pi sat, okay, plus this integral Pi sat to P, and this expression will get here. Okay. So, I can now rearrange this expression. So, if I rearrange this expression, the following I should get. Okay, let me correct this, this is going to be P. Okay. So, before I rearrange this expression, this right hand side can also be written as F sat pure I T. Okay. And why is that? Here this P is not the same as P here, because it is 0 to P sat. So, if I look at it, this should have been actually P I sat, corresponding to this basically T here, corresponding to temperature T here. Okay. So, this should be P I sat, okay, T. So, now we are saying that this itself is going to be only T, because once you say basically is saturation, it indicates that this corresponds to a specific temperature, that temperature. So, this is only dependent on just one variable T, due to the fact that this is a pure system. So, I will write here P I sat, again T here, plus this term. Okay. So, let me further simplify this. So, this is going to be RT FL pure I Tp divided by P can now be broken into two parts, one due to the contribution from 0 to P sat, divided by Pi sat T, plus the other contribution, which is from Pi sat P VIL dP. This is the first part of this, minus of Pi P. I can take minus outside the integral and make it here. This is going to be RT by P dP, which is nothing but RT ln P by P sat. Okay, so I can write this as simply, this is nothing but RT ln P by P sat. Okay. Now, I can further simplify this expression and rearrange this expression to make it a much more simpler looking expression rearrange, we obtain the following expression: f of L pure I at temperature Tp, this will be equal to this is equal to f of saturated figure f of liquid at saturation, okay, which will be only dependent on this T. Once you fix the T, the corresponding saturation pressure is fixed, and at that point the fugacity is also fixed, and the other term is basically the correction due to the change in the pressure from Pi sat to P VIL by RT dP. Okay. So, this is the term we got, which is a multiple of two terms due to the saturation fugacity, this plus the correction term. Okay. I can also make use of fugacity coefficient to express this term. So, I can write this as f of L pure I Tp. This is nothing but Pi sat at T and phi I sat T. Note that the definition of fugacity coefficient is nothing but phi I at T. P is nothing but f of pure Tp divided by P. So, basically the fugacity coefficient is nothing but f by P. Okay. So, now I can replace this expression in terms of the fugacity coefficient. I can write this expression as P I sat multiplied by phi I sat. Okay. These are both dependent on temperature. Okay. Then this term exponential Pi sat VIL by RT dP. Okay. Now, note that phi sat, note that phi sat is a function of T and Pi sat. Since the constraint due to the condition of the saturation, this can be written as simply phi I sat T. Okay. So, it is independent of, or it is dependent on only one variable. Okay. So, if you look at carefully, this expression here basically tells you that fugacity of the pure liquid I is equal to the saturated vapor pressure. So, if you look at very carefully, this equation tells you that fugacity of a pure liquid I is equal to the saturation pressure Pi sat corresponding to T multiplied by two corrections. The first correction, this is fugacity coefficient. Okay. So, this is basically fugacity coefficient of the saturated vapor, and what it's account for? It's account for non-ideality of the saturated vapor. So, that is a fugacity coefficient. So, it accounts for of saturated vapor. Okay. And then you have this another term. Okay. Now, this is, as I said already, this is nothing but, we call it often as Poynting correction. Okay. And what it accounts for? So, it accounts for compression of the liquid from Pi sat to P. Okay. So, this is exponential Okay, so it accounts for okay. So it accounts for compression from Pi sat to P, compression of the liquid from Pi sat to P. Often we try to approximate this term Poynting correction. So this approximation typically we give we make is PIL P minus Pi sat divided by RT. Okay. Now, what is the reason for such an approximation? Because we have taken this molar volume outside, which means we have assumed that the liquid is incompressible. Now, in addition to that, with other approximations which are which we can make use of, it depends on the condition. So, for example, approximation at low pressure, we can make use of I sat is equal to 1 approximately at low pressure, since it behaves like ideal system. So, we can as well as the Poynting correction factor is also close to 1. Okay. So, let us try to understand this. How does this approximation looks like for different systems? Okay. So, in order to understand this Poynting correction, or in general the fugacity, we will take an example. Okay. So, let us discuss the fugacity coefficient behavior for liquids at saturation condition by considering 4 molecules. So, this is an example. We have taken methane, nitrogen, propane, water, and in order to plot this on the same scale, we have made sure that we have taken the reduce the temperature. So, this is reduced. So, this temperature is nothing but T by Tc. Okay. So, in order for you to understand this, let me just provide more details. So, this particular point corresponds to a state condition where the liquid and vapor are saturated at a specific reduced temperature. So, once you fix this temperature, the corresponding it tells you that this it has a certain pressure, which of course I am not plotting here, but all this point are at saturation. And of course, with this, since the temperature is different, the corresponding saturation pressure would be also different. But since it is a saturation, we do not require Poynting correction, first of all. The second is that we have made use of the expression which we have derived earlier, and the vapor phase volumetric data from 0 to P sat has been used, and VL, the 0 to P sat volumetric data has been used. Okay. Now, if you look at this fugacity coefficient, it is something which is very clear that these are very much alike. That means they are more or less superimposable plots. The important thing is basically the fugacity decreases with increase in the reduced temperature. That means when the temperature is increasing and is approaching towards its critical point, the fugacity coefficient drops or decreases dramatically. Okay. But at a lower Tc is very close to 1, okay, which is very visible, particularly water. Okay, it around is close to 1. So, that means the approach towards ideality is visible at lower values of Tr. Okay. Otherwise, if you look at it at very close to Tc, there is a significant deviation from the ideality. Okay, from 1 to 0.7. Okay, that is a significant deviation. Now, let me also further point out a bit of this Poynting correction. Now, it is usually very small. This is the Poynting correction, usually very small at low pressure, but it could be very large at high pressure. To appreciate this point, let us consider molar volume of an incompressible fluid which is at 100 centimeter cube per mole at 300 Kelvin. Okay, so we are looking at only this term where we have put the molar volume at 100 centimeter cube per mole, and the pressure, this delta P we vary. So if we consider delta P, or the pressure in excess of saturation pressure 1, the Poynting correction is only this, okay, which is close to 1. But if you consider 10, it increases, but is not to that extent, is negligible. But one increase in another, increase by one order increases this Poynting correction significantly, and further increase by another order, the Poynting correction is like dramatically much higher. Okay, so thus it can be very large at high pressure. This is something which we must understand. Okay, so let me also try to give an example of a particular molecule. So let us consider liquid water. Okay, and here what we are going to consider is basically 3 temperatures, okay, which can show the breadth of the temperature from low temperature to temperature closer to critical point. And let's see what kind of behavior for fugacity we have for water. Now Tc is basically for liquid water, for water itself is 374 degrees Celsius, and what we are varying is the 3 temperature from saturation pressure to 414 bar. So let us look at this here. This is the very high temperature, intermediate temperature, and low temperature. Okay, so we have fugacity here as a function of the pressure of the system. Okay, so this point corresponds to the pressure, or this point corresponds to the state of this liquid vapor saturation at this particular temperature. Okay, so at this temperature the Psat is 213.3 bar. Okay, at this temperature the Psat is 16.89 bar. At this temperature the Psat is close to 0.0654 bar, and what we are doing is basically keeping the temperature fixed and changing the pressure. Now what you can notice that here in this case these are all compressed liquid data. Okay, from here to here these are all compressed liquid data, right? So at lower temperature the fugacity of the compressed liquid is almost or nearly equal to the pressure, total saturation pressure. Let me just restate this. So this is the fugacity here. So the fugacity of the compressed liquid is more nearly equal to the saturation pressure than the total pressure. We can see this statement very clearly. So for example, this is the fugacity, this is more nearly to this saturation pressure than the pressures here. Okay, so for example here also we can look at it. So these are the fugacity of the compressed liquid at very high pressure, but this is very close to the saturation pressure. And the other important thing is that at high temperature liquid water is no longer compressible, which is evident from these values, the fugacity, because it deviates significantly from here, which indicates that that very high temperature the compressibility cannot be neglected in Poynting corrections. Okay, so this is a very practical example considering the real systems in order to understand the effect of the pressure or at different temperatures. So we will stop here and we will continue our exercise of understanding this thermodynamic property from volumetric data in the next lecture.